the last talk today is by Terry Gannon from University of Alberta. Please.
Thanks. I'd like to thank Arthur and his team for organizing this this great conference. Arthur spoke yesterday about what defines a successful conference, and he said that a successful conference is one that creates new collaborations and stuff. And so, just speaking from my own perspective, I think this will be the case for sure. So I think it's been a really great. I'm honored to have been invited here. Right. So this is the thing I use to flick.
No, use the computer.
Oh, okay. Great. So I think we all more or less know what I'm going to talk about, but we use different languages. So let's start with the quantum group modular tensor category. We've seen these in lots of talks. It's been a source of lots and lots of examples. And so let's start. So the first example is going to be SL2 at level 4. So I dropped a Q from my USL2, but so Q will be specialized to a 12th root of unity. So 12 is 2 times 4 plus 2, and so this has anyons, simple objects that I'm labeling by the dimension of the corresponding SL2 representation. So 1 is going to be the tensor unit. 2, 3, 4. So 2 will be the fundamental representation, et cetera, et cetera. And so you have fusions that we all have seen before. For example, 2 times 3 equals 2 plus 4, et cetera, et cetera. One of the words I'm going to use a lot, and that we all will have different names for, is simple current. So this is just an anion that is invertible. So when you tensor by it just permutes the other simples. So for example, 5 times 5 is 1. So 5 is its own inverse. 5 times 2 is 4, et cetera, et cetera. We can condense we can condense the SL2 at level 4 through an algebra that's the sum of 1 and 5. So it's the sum of the unit and the simple current. And this kind of a thing moves you from SL2 to SO3. SO3 is just SL2 quotient, the center. And so in this in particular here, SL2 at level 4 condenses to SL3 at level 1. And so when you condense, you get a new modular tensor category. The new simples, the new anyons are, when you restrict down to the original category, SL2 level 4, they are 1 plus 5. So this will be the tensor unit in the new tensor category, 3 and 3 prime. So because the simple current fixes 3, 5 times 3 equals 3, that's a fixed point and it splits. And when it's not a fixed point, you get a sum over the orbit. So this is a baby example of condensation, a baby example of a quantum subgroup. So we can also use the conformal field theory language. And so there's a chiral conformal field theory. Conformal field theory, we'll talk more about this in a few slides, but a conformal field theory can be interpreted as 2 chiral halves, which are then spliced together. And so the chiral conformal field theory, or vertex operator algebra, is the SL2 at level 4, and you're extending this vertex operator algebra, and it becomes isomorphic to SL3 at level 1. Okay. So these are not meant to impress you. These are the boring extensions, the boring condensations, the ones involving simple currents. So here's a more interesting example: SL2 at level 10. So it has, I screwed up here. Its anyons, its simples are 1 up to 11, not 10. 11 is the simple current. This can condense through an interesting commutative algebra, a non-trivial commutative algebra, 1 plus 7. So it gives you the corresponding modular tensor category is isomorphic to C2 at level 1, and the new simples, again, you restrict so C2 at level 1, as you may know, has 3 simples, and so if you restrict those 3 simples, you get the things I wrote down there. So this is a much more interesting one, and so we call those. The language I sometimes will use is local A modules, where A is your algebra, And of course, you're restricting down to the category you're starting with, the original modular tensor category. And so your VOA that you start with, which will correspond to A1 at level 10, will extend to become a VOA at C2 at level 1, of course. And you can, whenever you have a bigger algebraic object, you have a smaller algebraic object inside a bigger one, then you can restrict representations, modules for the bigger guy to the smaller one. And so that's this, that's the stuff we've written down there. Okay, so what's a quantum subgroup? Well, what I'm going to mean in this talk anyways is it's a condensation of one of these quantum group modular tensor categories. So you choose your favorite Lie algebra at some positive level. That's a quantum group modular tensor category. And then you try to find algebras, commutative algebras that you can condense to get some other modular tensor category. The new modular tensor category may or may not have anything to do, it might not have anything to do with Lie algebras, although it often does. Okay, and so the generic or boring condensations are through algebras that are sums of simple currents, just like the SL2 at level 4 example. So for example, for SL2, 1 plus k plus 1 will always work at least when k is a multiple of 4. So those are the ones that we're not interested in. We completely understand them. And so anything else is an exotic quantum subgroup. So we want to know about the exotic quantum subgroups of these things.
Is the simple current always boson?
A simple current is always what, sorry?
Is always boson? It means with a topological spin 1. Because if it's not, it may not be able to condense.
No, that's right. So you can't. So for example, for SL2, you can't condense it when the level is odd, for example. So yeah, so simple currents. So they sometimes work. They sometimes give you something. They sometimes don't. But we understand completely.
Okay.
All that. Actually, I need questions because that's what fuels me. Otherwise, I just start putting myself to sleep. So it's great to. So this is one of the questions that was mentioned by Pavel and Victor on Monday to try to understand the exotic subgroups of the A series, but whatever. Okay, in the beginning, there was Capelli-Itzykson-Zuber. So this was in 1986 or 1987 or something. And so what they're interested in doing was classifying all conformal field theories, which are rational with respect to an SL2 symmetry. So who knows what that means? Actually, we're going to find out what that means. And so, so conformal field theory, just to very quickly remind you, is conformally invariant quantum field theory. I'm sure you all know about this. We're always in two-dimensional space-time. And so as I said earlier, the full CFT, the true CFT, contains holomorphic quantum fields, and it contains anti-holomorphic quantum fields. So it has two chiral halves, they're called. And the full CFT is recovered by splicing together these two chiral halves. And so mathematically, you can interpret a chiral CFT in different ways. We don't need the conformal field theory language. I'm just saying this because sometimes when I speak, I'll be using this sort of a language. But if you're not familiar with it, it's not at all important. So chiral CFT, so you can interpret, I'll use the VOA language periodically. And so what a vertex operator algebra is an algebra of vertex operators. Vertex operators are quantum fields. So this is just an algebra of quantum fields. So what Capelli-Itzykson-Zuber did is they focused on the VOA for SL2 at level K. So these are very, very, very simple VOAs, amongst the simplest that exist. And so physically, they are Westmino-Witten models. In fact, all these quantum group things are going to be Westmino-Witten models. And so in this case, it's strings living on SU2. And so what they're interested in is conformal field theories whose chiral halves both contain this VOA. With finite index, whatever that means. Okay, so a representation theory of VOAs is described by a modular tensor category. So that's how the modular tensor category arises in this language. And so I'm not going to get into this because we don't need it, but you can see the modular tensor category stuff directly from the VOAs. Some of it is easier to see than others. So for example, the graded dimensions, the modules of your VOA are infinite dimensional, but they come naturally into finite dimensional pieces. And so if you look at the graded dimension of this, then these transform like modular forms with a multiplier. That multiplier is the modular data. So this is how modular data in your modular tensor category can be seen from your VOA. And so here's the formula that you get. But as I say, we're not going to use that. Okay, so this is the modular data for SL2 at level K. And so what it is in general is an alternating sum. The S matrix will be the alternating sum over the vowel group. So here the vowel group is sim2. And so you get a sign. You get alternating sum of exponentials. It reduces to a sign. And so you get something similar for every all of these, for any of these Lie algebra VOAs, similar S matrices. Okay. So I'm just trying to explain how to think about what Capelli-Itzykson-Zuber, how they thought about this question. And so you get these two chiral algebras acting on your space of states for your conformal field theory. And so your state space is going to decompose into a sum of these finitely many representations. And so if you look at the graded dimension for this, then you get something that is called usually called the modular invariant partition function. And so if you look at the coefficients of this thing, so the chi's, as you may recall, are these characters, these graded dimensions of the modules of your VOA, in this case, SL2 level K. And you see sum over all of them. It's a sesquilinear combination of them because you have these two halves. And the coefficients, this Zij, is it's a matrix which is positive non-negative integers because it counts. It counts how many sectors in your theory transform in the appropriate way under these two chiral algebras. There's a unique vacuum. You can see when I do this, that's good. And then it commutes with modular data. It has to be modular invariant. And so what they did was that's what they interpreted their problem of trying to find all full CFTs that see SL2 level K. They interpreted it as a question trying to try to find all of these modular invariant partition functions. So certainly it's not the same. The two questions are not the same, but this is a big hunk of it, and that's how they interpreted the problem. Okay, this is their answer. And so what you get is a three series. So the first one up here is it's always going to work. So it's just the boring one. You just have the sum of, so it's just the one that corresponds to anyways, it's the obvious one. So the identity matrix always works. It satisfies those three rules, and this corresponds to the identity matrix. You have two others that are a little bit more interesting. You can see, though, that they're involving simple currents. So chi minus 1 or k plus 1 is a simple current here. So you can see that this thing is involving, so these two terms here are simple current images of each other. So these two have something to do with simple currents. So they're very generic and they exist for half of the levels. And then you have three oddballs. So here they are. And so the boring one, the identity matrix one, corresponds to a string on SU2, the Vesmino-Witten model. A string on SO3, which is SU2 quotient at center, as I said before, a string living on that gives you these kinds of, that's what its partition function is. And then you get SP4, string living on SP4, string living on G2 are two of these other things. So these will be quantum subgroups in the way that I used before. These are pure extension things. They're sums of squares. And then you have this oddball one in the middle. Okay, and so this was one of the most celebrated results in conformal field theory. Well, to me, to be perfectly honest, it looks like random noise. Like how are you supposed to see anything in this list? For me, I don't see anything in this list, but actually they did. Or actually Victor Katz did and told them. And actually Victor Katz saw a joke, thought it was a funny joke to say, your classification sure looks like ADE. And then that's what all he said. And then so you can see ADE here. You can see there's kappa equals 12 is the Coxeter number of E6. Kappa equals 18 is the Coxeter number of E7, and this is E8. And you can look at the diagonal terms. For example, you have 1, 1, you have 7, 7, you have 4, 4, 8, 8. These are the exponents of E6. So actually you see there's some connection to ADE, but actually Vic Katz told me that it was just a joke. He said it was a joke, but fortunately he didn't tell Capelli-Itzykson-Zuber that this was a joke. He thought it was obviously a joke. And so they took it seriously. And so this motivated them, as you'll see. It was great. It was great. It was a great observation, a great joke, and all that. Right. And so we'll see consequences of this. So this is what ADE means. It means the simply laced Lie algebras. So here are some of the simply laced. So some of the things that fall in the ADE pattern. We'll come back to this. It's really an important observation, but let's ignore it for now. So an obvious question is, what about other algebras than SL2? SL2 is the baby Lie algebra. Well, how about the other ones? The answer for SL2 turned out to be kind of interesting. Maybe we should look at the other ones. And so there's lots of other ones that we could look at, but they have lots and lots and lots of anyons. It grows with the rank, polynomially with the rank, the number of irreducibles, the rank of the Lie algebra. And so I'm writing down here the S matrix for A2, but again, this is totally useless. We're never going to use this. I'm just writing it down to impress you with a complicated formula. So you can see here that, so the Weil group of SL3 is Sim3, and so you have an alternating sum of those 6 elements. You have exponentials that are added and subtracted from each other. So there's a pattern to these S matrices, but okay. Well, so Capelli-Itzykson-Zuber used very straightforward methods, but you can't do that. The arguments don't generalize. And so one of the key ideas in pushing this a little bit further was the observation that these S matrix entries lie in a cyclotomic field. So cyclotomic field just means you have some root of unity. This is the nth root of unity. And you look at all polynomials in that nth root of unity. So C squared minus 12C plus a half. So your coefficients of your polynomial are going to be rational numbers, and together they're closed under addition, obviously, and they're closed under multiplication, obviously. They form what's called a field. And so it's called the cyclotomic field because it has to do with circles. And so how can you exploit the fact that this lies in a special field? Well, one of the things you could look at is that you look at the symmetries of the cyclotomic field. So they're very simple. They behave in a very simple way. So they'll take this cyclotomic number to this cyclotomic number, where L corresponds to some number between 1 and n that's coprime to n. So those are the symmetries of this. So why do we care? Well, because there's a geometry. Lie theory is just beautiful, and because everything touches Lie theory. Lie theory touches everything, I should say. And so in particular, geometry touches Lie theory. And so the affine Weil groups that are under control of the theory here, there's the geometry of them tells you that they're going to see Galois. And so so you end up with some little pattern here. So you end up with a permutation of the anyons corresponding to each symmetry that you've chosen. And the S matrix knows about this. So these epsilons are signs, plus or minus ones, and so you wrap around. So the same thing happens for any modular tensor category. But here you have geometry, so you know what this permutation is. You have very good control over it. So why in the world do we care? Well, actually, this is really important, and it's an important part of my talk, actually. And I have to quickly speak, right? So so I can't get into the details because I'm out of time. But because it's a symmetry, you could just play around with the fact that your modular invariant has to respect this symmetry. I mean, anyways. There's an argument on this slide that gives you a very powerful selection rule that corresponds to Galois, and so it's a really constraining thing. And so you can redo the A1 class. The A1 classification of Capelli-Itzykson-Zuber took 30-some pages, and you can redo it in a page or two. And the key result is the key lemma is just this, is how is this Galois thing. So once you have that, then that explains all the possible extensions, and you're basically done. Okay, and so so you can use Galois to do the A2 classification, and you get for series, you get some exceptionals. Oops, you get some exceptionals, and whatever. So there's no ADE here, but there was a great observation that was made by well, it started with Philippe Rouel in a library in Dublin, but I don't have time to get into that story. And it connects Jacobians of Fermat curves to this classification. So solving the Galois symmetry selection rule for A2 is equivalent to a Kolbitz-Rohrlich argument for the Jacobians of Fermat curves. So it's the same. It was the same question that we both had to answer independently, of course. And there's no published classifications for the other Lie algebras. So you need Galois is still powerful, but it's not good enough. And so you need other ideas. And so the other ideas come from this ADE classification. So I have less than 10 minutes, right? Okay, great. So I can start backtracking and tell you about this Dublin library. No, I'll try to respect as much as I'll try to respect this, of course. So here's an example, and maybe I don't have time to get into this, but this is the most famous ADE pattern. So ADE is a pattern that that lies all over mathematics. It has to do with paramphobenius theory. So the graphs, the matrices that have largest eigenvalue less than 2 or equal to 2, and so the most famous example of this are the Mackay graphs. So you look at the finite subgroups of SU2, and you can draw graphs based on the representation. So the nodes of this graphs will be the different representations, simple representations of this finite subgroup, and then edges between these have to do with when you tensor, you have a special representation, this defining one in 2 dimensions coming from the embedding of this group into SU2, and you tensor that special one with all the other irreducibles, and you draw edges connecting them when you decompose it into a sum of irreducibles. And anyways, you get a graph. It turns out for the binary icosahedral group, it's a group of order 120. It turns out that it's E8 or extended E8, et cetera, et cetera. By the way, I asked Mackay how he came up with this thing. And what Mackay did was he added up. So if you add up the labels on this, so the labels on your Dinkin diagram, you get, so you know what that means. That's the Coxeter number, which has all kinds of meanings. What if you add up the squares of these numbers? What's that going to be? And so when Mackay did this, that got him thinking, and that's how he did it. So when you do it here, you get 120, which is the order of the binary icosahedral group. And anyways, that's how he did it. You have to play. Okay, so obviously it's highly suggested there should be an interpretation for the Capelli-Itzykson-Zuber graphs. They're saying that we get this ADE correspondence. Well, we should be able to see the edges on these graphs. And so this led Zuber to the notion of a NIMREP, a non-negative integer representation of the fusion ring. And so for these extension type things, the condensation examples, the ones that I'm focusing on in my talk, the nodes of these graphs are going to be the rep A modules, and you again get a natural tensor product there. And anyways, I don't have time to get into this, but you get a representation of the fusion ring, and so for Zuber it was experimental, but then the subfactor community, Yasu and others, dove into this and really pushed it far, brought in lots of new ideas, and then Victor did us all a favor and translated it into categorical language, which is something that you don't have to. It's much easier to learn what's really going on. And so the result is module categories. So the modern way to think about the possible full CFTs that you splice together from these this VOA, these chiral VOAs are called module categories. And so so you can think of a fusion category as a categorification of a ring. A modular tensor category is a categorification of a commutative ring. A module category is the categorification of module of a ring. And that's where the name comes from. And so anyways, so the NIMREP is just the combinatorics of the module category, just like the modular invariant is the combinatorics of another aspect of this. So a module category for us is a triple. So what you have is your original starting points, for example, SL2 level K VOAs. You have 2 of them. you have to, you write down an extension of one of them, an extension of the other one, which might be trivial. By extension, again, I mean condensation. And then you have a tensor equivalence between the corresponding modular tensor categories. So that triple is what a modular category is. That's the most convenient picture from our point of view. Okay, and so Fuchs, Runkel, Schweigert, and other people explain how modular category, this picture gives you the CFT, the full CFT from the chiral halves. And so from this point of view, what Capelli-Itzykson-Zuber were doing, we're just classifying a combinatorial part of the story, namely the modular invariant. Really, there's module categories. You have to really do the categorical stuff. We'll talk briefly about that in a few seconds. So the way to get from this point of view, the way to see your modular invariant is you have your left extension, saturation, and so that's going to give you restriction map of branching rules, and the same for the right. And then you have your permutation coming from your tensor equivalence. So this is the triple that we're talking about before. This is what it looks like combinatorially. And then if you put it together in this way, or maybe I have it wrong and the wrong thing on the wrong side and transpose on the wrong side, but it's something like this, then that's your modular invariant. So the branching rules are intertwiners from the two different modular data, the extended to the other one, or vice versa. Right, and so the categorical version of this, so doing really the classification was done by Galois and Victor 20 years ago. Okay, so right, so if we look at it from the triple point of view, the A series, the silly ones, the ones that correspond to the identity matrix, are trivial extensions and the identity equivalents. And half of the Ds are trivial extensions but non-trivial equivalents, and the other half are non-trivial extensions and the identity equivalents. And this one here, the E6 one, corresponds to its condensation, an extension. The 18 is the interesting one, the E7 one. It corresponds to an extension and non-trivial equivalence. And E8 is another pure extension type. Okay. And so if we want to generalize Capelli-Itzykson-Zuber and see what goes beyond ADE, what we have to do is choose a Lie algebra and a level, and we get our corresponding VOA, or we get our corresponding category. We have lots of these, and we've already talked about this. So this is, we want to do the module categories for this thing. Right. So what we want to do is find all possible extensions of our Lie algebra VOA, or all possible condensations of our quantum group modular tensor category, and then all possible equivalences of those extensions. But because of the connection, the analogy with finite subgroups of SU2, that's where the name quantum subgroup comes from. So instead of being subgroups of SU2, they're sort of subgroups of quantum groups, sort of, not really, but okay. So there's one generic source. These are the boring ones. These are the ones that come from simple currents, the invertible anions. And so in the language of, in the Capelli-Itzykson-Zuber list, this gives you the A series and the D series. So all of the series are the generic ones. So as I said before, they're not interesting. They're well understood. And so by an exotic module category, we mean anything other than these. And so there was a breakthrough recently. Kane classified all of these autoequivalences for basically all of these modular tensor categories, these quantum group modular tensor categories. And he also has partial results. He's done the A series for the simple current extensions. So and so it's inevitable that this will be completed soonish. And so this is a major part of the story. But what it means is the issue now is understanding the extensions. So understanding the condensations, the other part of the story, or 2/3 of the part of the story. And so I'm going to focus on that. So when I say quantum subgroup, I mean of extension type. Okay, well, of course, A1 and it turns out A2 are done, but basically that's it. So Ocneanu announced, Ocneanu announced without details for A3 and A4 and perhaps some other ones, but we, you know, there's no proof. The proofs haven't appeared. At least I've never seen them. And so, but there's a new ingredient that Ocneanu introduced, and this is induction. So it's induction. So far, all I've mentioned are branching rules. All I've talked about are restrictions, but a much deeper part of the story is induction. So it started in the subfactor world, and it's called alpha induction there. So Yasu and others were introduced this into that story, and it's a vital part of the whole story. And so I'm definitely running out of time, so I'll do this very quick. So your induction takes you, so we have some kind of a condensation, we have some kind of an extension. So this is the E8 one. It's a condensation of A1 level 28 into G2 at level 1. And so if you take modules here, anyons for the smaller VOA, then they induce, in general, not to the G2 one, the local ones, the modular tensor category here, they go beyond it. So they go to rep A, so the soliton category. So it's a fusion category and not a modular tensor category. And so the modular tensor category is going to correspond to the local ones, the local A modules. Anyways, this is what the answer looks like for E8. So now we understand really the connection of the ADE diagrams to the Capelli-Itzykson-Zuber classification. Once again, the lines here correspond to the multiplications, just as they did for Mackay. And so these numbers here are the restrictions of the A module, the soliton or whatever, for G2 level 1, restricted down to A1 at level 28. That's what the top numbers are. The taus mean that they're twisted or solitonic. And these numbers here are the Deacon labels shifted by the Weil vector. Anyways, so you get E8, as you should. Right. So this is the key to Ocneanu's work on the classification stuff. So it came through it. So it was never announced, at least not clearly enough for most of us. I think Victor listened carefully to a talk that Adrian gave and extracted more information than Adrian ever meant to be extractable, and came up and guided his former PhD student Andrew Shuprai to write down to explain what was going on in Ocneanu's head, I think. And so so this deserves the name Ocneanu's lemma, I think. But the first time I saw this written down was in the paper Andrew wrote. By the way, Andrew is he's my postdoc right now. He's on the job market, so he was the key to a deep problem that was basically languishing in mud, smelly mud. He came up with the first real great contribution in 20 years or so. So he's on the job market. Okay, so you get some. So so this talks about inducing. So you start with your SL2 level K or whatever. So it's the module I'm gonna label with lambda. If lambda is small in some sense, if its Dinkin labels are small compared to the level, there's an explicit. This is what it means, but who cares? If it's small enough, then when you induce it, the result will be simple. So this was Ocneanu's observation. The proof is 2 lines. Here's the first line. The second line I'll save for you to do as an exercise. It's like Schur's lemma. It's one of those things that is easy to prove, but the repercussions are significant. And if you're clever enough, and Andrew is clever enough, then you can you can use this to come up with a bound for where exotic quantum subgroups can arise. And so Andrew worked it out for C2 and he got 20,000 or so, and he worked it out for G2 and he got 18 million or so. So if your level is bigger than 18 million, then there are no exotic subgroups. All subgroups just come from, all condensations are simple current ones, so completely boring ones. And similarly for C2. And similar arguments, they weren't fleshed out, but it's clear that they will work for other algebras. And Andrew's estimate is the bound grows like 3 to the power of the number of roots. So for E8, for example, it's going to be a Google. So even for G2, this is hopeless. These numbers are hopeless, but it's really significant. It tells you that it's a finite problem. There's only finitely many exotic quantum subgroups. Right. And so my contribution to this is to make this much more effective. So I brought in the Galois thing, which I think is a really important part of the story as well. And so again, the Galois automorphisms correspond to these integers that are co-prime to the level, basically. Then if you found one of these co-prime things that's small enough, bigger than one, obviously, but otherwise small enough, and that you can make that explicit. Then I'll try to make that explicit in a few seconds. Then the Galois orbit, where it sends the unit. So I'm calling the unit rho here for whatever reason. This is 1. So L times 1, the Galois image where the Galois sends 1, the unit, is going to be. It's going to be like this. It's going to be this formula. This is the formula for it in terms of the Dinkin labels. And so by Galois symmetry that I didn't really show you, this thing here is necessarily going to appear in the modular invariant. And so if rho is really small, I'm not sure what that means. Then anyways, if Ocneanu's inequality holds, then the induction of this object is going to be simple. And so in that case, what we get is this induction is going to be a local representation it's going to be simple, and it has to be, a piece of it has to be local, and therefore the whole thing is local. And that's significant because all of the twists, when you restrict down to SL2 level K or whatever your underlying thing is, they have to have the same value of the twist. That's just commutation with T. And so you can describe what the restriction of the induction is going to be. There's a simple formula for it, and it's easy to show that it's hopeless. So I'm definitely over my time. Sorry about this. So the punchline is there's an inequality. I wrote down it in too strong of a form, but it's a neat enough inequality that I'll just write it down very quickly. So if you can find the smallest prime, which is co-prime to the level, or in half the time it's 2 times the level, or for G2 it's 3 times the level. This is the shifted level by the Coxer number. If this thing is less than 1/2 plus square root of 6 times the level over the dual Coxeter times the dimension of your Lie algebra plus 1/4. So if the smallest prime that's co-prime to your level satisfies this inequality, then there are no exotic quantum subgroups. So it has to be any condensation has to be through simple currents. And so so you can use that fact to prove, I'll leave it as an exercise, to prove that the bound that you get isn't 3 to the power of the number of roots. The bound is the cube of the rank of the Lie algebra. So it's a very small bound. And so anyways, if you use the stronger statement, then you can push it even smaller, and it grows like the rank squared, the number of bad levels. So so the levels that survive the punchline are written here for the Lie algebras, the A series up to 6 and the other guys. And so just to choose a random example, A4 will have 21 levels that survive this. The bold face are where there actually is a quantum an exotic quantum subgroup. So this is still not super efficient, but it's not that bad actually. And now it's easy to kill off these remaining examples, and so you can do that, and you end up with my paper, which will be released shortly, does the classification of exotic quantum subgroups for ranks, for everything of up to rank 6, up to including rank 6. Okay. So here's the answer. So don't trust these numbers, because every time I count up, I get a different number than 71, but 71 is the average. And so so there's precisely 71 exotic quantum subgroups. So exotic condensations of these things up to including rank 6. 51 of them are of the kinds that we saw for SL2. They're things like A1 level 10 contained in C2 level 1. So not just the smaller one, but the bigger one is of Lie type. And so almost all of them are of that type. So these are well understood also. And there's other ones that are quite well understood. And there's 4, I believe, that are truly exotic. So again, these numbers you shouldn't completely trust, but in a week or two, the paper will come out and you'll be able to trust those. And so this is so you have to require ad hoc methods. And so the methods that I've used are VOA methods. So the VOA people spent a lot of time constructing exotic VOAs that turn out to be exactly what I need to prove the existence of VOA extensions, which are equivalent to quantum subgroups. And so the moral of the story is these VOAs of Lie type have very few extensions. The modular tensor categories of quantum group type have very few condensations, apart from the obvious ones coming from simple currents. And so what does it all mean? What comes after ADE and Jacobians of Fermat curves? Well, actually, that's not for me. I can't even see ADE. That's for maybe one of you. So you look at the answers that we get and see some kind of a connection. What generalizes Jacobians of Fermat curves? Something involving Shimura varieties? I don't know. So this is Lie theory. It's Lie theory and string theory. So you know it's going to be beautiful. The answer has to be beautiful. So anyways, sorry for going over time. That's it.
So questions?
So thank you for telling us all these beautiful results before they're published. And you talked about the consequences for mathematics. Do you have any conjectures about consequences for physics?
Yes.
Yeah, I don't know the answer to that. So basically, what I would ask is, I'd say, Capelli-Itzykson-Zuber, how is that used in physics? So it's one of the standard results. Any review of CFT will include that somewhere in it. So it clearly, so this is on, I would imagine that it should also have some kind of implications for the physics. But actually, I haven't thought about it.
Okay, other questions?
Yeah, hi, Zheng Wang. So your G2 level seems surprised me. Are you sure it's a 7 and 8?
What I might not have made it clear. Let's go backwards.
3 is there's 1.
Exactly. So what? Here, let's go
What's the
back.
other
Level plus the dual box.
Right. So that's what I've been. Yeah. So in these things, I've added the level. So I'm using kappa, what I'm calling kappa, which is the level plus dual Cox there.
Okay. Other questions?
So here's the paper. So it makes a sound when it hits the tabletop.
Terry, so for those the truly exotic ones, are the VOAs you get from the extension of not of Lie type, or are they already known?
So they're in some cases they're like one of them is A6 at level 7, and so that extends to a holomorphic, one of the holomorphic C equals 24 VOAs. So that one, the corresponding modular tensor category is 1 vec. But there are some that are more subtle. I think so. I know all of the modular tensor categories. I can identify them, but they're not all of Lie type, of quantum group type, but they're so in one of the cases it's a Galois associate of one of them and stuff. So like for example, Kane's work for the A series for sure. Kane's work. So Kane's only fleshed out his program for the A series where it's complete, and there we have. He's done enough stuff that we can handle all of the triple. So I handled the extensions, and Kane handles all of the possible equivalences between these extensions. So they're all of close enough to Lie type that you can, from stuff you know about Lie type, you can carry it over.
Okay, other questions?
This is Victor Ostrik. So when can we hope for answer like this for E8?
Yeah, so right. So I have a limited tolerance and ability when it comes to computers. And so So I probably will need maybe some help, but yeah. So as I said, the things grow like the cube-ish of something like the cube of the rank 8 in this case. It'll be a little bit bigger than that, but and then you use other arguments to quickly get it down. This is just that thing that I wrote down there is just the crude thing. So you can enhance it a little bit, and so you chop it down, and then there'll still be some harder work, but I talked it over. So the answer, I'm not going to stop until someone, hopefully not me, does the VE8 thing. So for sure, I want to get up to rank 8. This paper is just going to do 6. But the A series. So your question and Pavel's question on Monday was about the A series. So know the full answer. So it's you can't really see it from here, but it's not. There's no pattern to my eyes that's obvious yet. So I think that's one that's maybe worth pushing a bit further. The A series is very friendly this way, so you can really push it a lot further than 6. So maybe get up to 16 or something, and then someone else will probably see what's going on.
I mean, we asked about A series just to be concrete. I mean,
Yeah, right.
Other questions?
By the way, this was my PhD problem. So my supervisor thought Capelli-Itzykson-Zuber did A1. Surely, I can't believe that no one has done the rest. So your project is to do the classification for all the algebras. So that's why I've looked so depressed over the last 30 years or whatever, is because I couldn't even do my thesis problem. But now I feel a lot happier.
So I have a question. So there, as far as I remember, there were some number of bottles of champagne offered for solving this problem for Lie algebra or of type AN, and the number was some function of n. So
wow,
what was that function? And did you
we
get
should find? Yeah, that's right. I want to hear about this. I want to learn about this. It was between Zuber and Ocneanu or something, wasn't it? Or?
That's right.
Yeah, so
apparently Ocneanu took all the bottles and did not provide proofs. So
that's right. So I'll be knocking on his door soon.
Yeah, but I think function was growing fast with the rank of the group. So I'm not sure. Okay, other questions? Okay, so let us thank Terry.